Ready to test your multi-source graph skills? Pacific Atlantic Water Flow is a Pattern Mastery 100 standout and a frequent challenge at Google and Amazon for Grid DFS/BFS mastery. More than 30% of candidates stumble on multi-source propagation or state tracking. Master this and you'll be ready for any two-way reachability problem in grids or graphs. Let's solve Pacific Atlantic water flow using the basic approach, a robust method for systematic, interview-ready solutions. Given an MXN grid of heights, return all coordinates where water can flow to both the Pacific and Atlantic Oceans. Water can flow from a cell to neighboring cells with equal or lower heights. The Pacific touches the left and top edges. The Atlantic touches the right and bottom edges. 2D grid of integers, heights list of coordinate pairs, row, col, where water can flow to both oceans. Think about rainwater flow on a terrain map. Where could water reach both rivers? Interviewers might ask, how would you find all meeting points in a network from multiple start sources? What's tricky? Water flows uphill in this reverse sense. We can visit a cell if it's equal/higher than the previous, simulating water flowing down from it. Need to find cells that can reach both oceans, not just one. Must avoid redundant searches, propagate from oceans inward, not from each cell out. For each ocean, mark all cells that can flow into it. Pacific, start from all top and left edge cells. Atlantic, start from all bottom and right edge cells. From each ocean border, use DFS or BFS to move to neighboring cells of equal or higher height, reverse water flow. Collect cells reachable by both DFS runs. The intersection is the answer. Let's clarify. 2 visited sets, one for Pacific, one for Atlantic. Each DFS only goes uphill to equal or higher height. Final answer is the intersection of the 2 sets. Edge cases. Empty grid. Return. Single row/column. All cells touch both oceans. Flat terrain. All cells can reach both. Initialize 2 visited sets for Pacific and Atlantic. For all Pacific border cells, top row, left call, DFS/BFS and mark all reachable. For all Atlantic border cells, bottom row, right call, DFS/BFS and mark all reachable. Result equals intersection of both visited sets. Let's try to implement it using solution 1. This line starts our solution class. It's like creating a container to group our method that will solve the Pacific Atlantic water flow problem. Here we define a function called Pacific Atlantic that takes one input, heights. Heights is a 2D grid where each cell represents the height of the land at that position. We want to find all positions where water can flow to both the Pacific and the Atlantic Oceans. This line figures out the size of the grid. M is the number of rows. N is the number of columns. We'll use M and N a lot when we move around the grid so we don't go out of bounds. This is a simple constant time operation, O1. Here we create a 2D grid called pack with the same size as heights. Every cell starts as false, meaning we don't yet know if water from this cell can reach the Pacific Ocean. Over time, we'll mark some of these as true. Building this grid takes OMN, time because we touch every cell once. And this line does the same thing, but for the Atlantic Ocean. ATLIJ will be true if water from cell I, J can reach the Atlantic. Again, this creation is OMN. So our setup so far is linear in the size of the grid. Now we define a helper function called DFS, short for depth first search. It will start from a cell, I, J, and mark all cells that can flow to a particular ocean, PAC or ATL, by moving uphill or flat from the ocean edges inward. First thing the DFS does, it marks the current cell, I, J, as true in the ocean grid. That means, yes, this cell can reach this ocean. This loop is our way of exploring the 4 possible directions from the current cell. Down, 1, 0, up, -1, 0, right, 0, 1, left, 0, -1. We'll use these offsets to compute neighboring positions. Here we calculate the neighbor's coordinates. Ni is the neighbor's row, NJ is the neighbor's column. This if line is doing several checks at once to decide if we should continue the DFS into that neighbor. 0 less than equals Ni less than M and 0 less than equals NJ less than N. This makes sure the neighbor is inside the grid, not outside the map. Not ocean Ni NJ. This ensures we only visit the neighbor if we haven't already marked it as reachable. That prevents repeated work and infinite loops. Heights Ni NJ greater than equals heights IJ. This is the key water flow rule. We only move from lower or equal height to greater or equal height. We're simulating the reverse direction. Instead of water flowing down to the ocean, we start from the ocean and move uphill or flat. If we can move from the ocean inward to a cell, it means water from that cell can flow back out to the ocean. If the neighbor passes all those checks, We call DFS on that neighbor. Now we start from the Pacific Ocean's edges. This loop goes over all columns J in the top row. For every cell, 0, J, in the top row, we call DFS with the pack grid. This simulates water reaching the Pacific from the top edge and then flowing inward to all cells that can flow back to it. Next, we handle the left edge, which is also touching the Pacific. We call DFS for each cell, I, 0, in the leftmost column. This again spreads inward from the Pacific side. Now we switch to the Atlantic Ocean side. This loop goes over all columns J in the bottom row. For each cell, M, 1, J, in the bottom row, we call DFS with the ATL grid, spreading inward from the Atlantic edge. This marks all cells that can reach the Atlantic via paths going downhill to this border, in the normal water direction, or uphill when we reverse it like we're doing. And now we cover the right edge, which also borders the Atlantic. We call DFS for each cell, I, N, 1, in the rightmost column, again marking all cells that can eventually flow to the Atlantic. So to recap, top and left edges feed the Pacific DFS, bottom and right edges feed the Atlantic DFS. Across both Pacific and Atlantic DFS phases together, the total time is still OMN, because each cell is visited at most twice, once per ocean. Now we create an empty list called result. We loop over every row I in the grid. And for every row, we loop over every column J. So together, these two loops scan every cell, I, J, in the grid. This scan is OMN. Here's the key check. We look at cell, I, J, and see if pack IJ is true. It can reach the Pacific. ATL IJ is true. It can reach the Atlantic. If both are true, then water from this cell can flow to both oceans. That's exactly what the problem is asking for. If the condition passes, we add I, J to the result list. Finally, we return the result list, a list of all coordinates that satisfy the Pacific and Atlantic condition. Overall, our time complexity is DFS for Pacific, OMN, DFS for Atlantic, OMN, final scan to collect results, OMN. So the total time complexity is OMN, linear in the number of cells in the grid, which is very efficient for this type of problem. And that's how this algorithm works. It first sets up two grids to track reachability to each ocean, then uses DFS from the ocean borders to mark all cells that can flow to each side, and finally collects the cells that can reach both. Efficient, simple, and elegant. Let's test our function using this height matrix. Each number represents the elevation of land at that grid cell. Higher numbers mean higher ground, lower numbers mean lower ground. Our goal is to figure out which cells can send water to both oceans. The Pacific touches the top and left borders. The Atlantic touches the bottom and right borders. Water can flow from a cell downward or sideways, as long as the next cell's height is less than or equal. But remember, since we ran DFS from the oceans inward, our rule flips. We only move from the ocean to a neighbor if the neighbor is higher or equal, meaning water could flow downhill back to the ocean. Now, here's what happens in this test. The Pacific DFS explores from the top and left edges, marking all cells reachable uphill or flat. The Atlantic DFS explores from the bottom and right edges, doing the same. Finally, we intersect both sets of reachable cells. Any position marked true in both grids means water from this cell can flow to both oceans. And the program outputs exactly these coordinates, perfectly matching the expected result. Each of these cells sits on a path where water can go downhill toward both the Pacific and the Atlantic. For example, 0, 4 is at the top edge and can flow right toward taller cells that eventually descend to the Atlantic. 3, 0 and 4, 0 are tall on the left Pacific edge and can climb up towards cells that drain to the Atlantic side. 2, 2 is on high ground, able to spill in both directions. Everything checks out beautifully. So, our implementation is correct. The algorithm effectively finds all cells with dual ocean reachability using two DFS sweeps, efficient and accurate. Now let's try another implement approach using solution 2. This line starts our solution class, the outer container holding our optimized Pacific Atlantic function. Here we define Pacific Atlantic, which takes heights, a 2D grid of land heights. Our job: find all coordinates where water can flow to both the Pacific and Atlantic Oceans. This gets the grid dimensions, m equals rows, n equals columns. We use these to navigate safely. This is a constant time O1 step. We create the pack matrix, same size as heights. Every cell starts false. We haven't confirmed this cell can reach the Pacific. We turn entries true as we find reachable cells. Building this is OMN. This creates the ATL matrix for the Atlantic. All false at first. We mark true where water can flow to the Atlantic. Also OMN. We set up Q_pack for the Pacific. We'll use BFS, so we need a queue to process cells level by level. And Q_ATL is the Atlantic queue. We'll do one BFS from Pacific borders and one from Atlantic borders. Each cell enters each queue at most once. BFS is OMN, per ocean. We initialize the vertical border cells touching both oceans. This loops over row index I. We add the left column cell, I0, to the Pacific queue. It touches the Pacific. We mark pack I0 equals true. This cell reaches the Pacific. We add the right column cell, IN1, to the Atlantic queue. We mark ATLIN1 equals true. It reaches the Atlantic. Now we loop over column index J for the top and bottom edges. We add top row cell, 0J, to the Pacific queue. Top row borders the Pacific. We mark pack 0J equals true. We add bottom row cell, M1J, to the Atlantic queue. Bottom row borders the Atlantic. We mark ATLM1J equals true. Now we start the Pacific BFS. This loop runs while Q_pack has cells. We pop cell, IJ. We know it reaches the Pacific. We'll try to walk uphill to neighbors that can also reach it. We loop through the 4 directions: down, up, right, left. This is O1 per cell. We compute neighbor coordinates NI and J. We check. Inside bounds, not already Pacific reachable. Neighbor height greater than equals current height. Each cell passing this is processed at most once. So Pacific BFS is OMN. We mark pack NI and J equals true. And push it into Q_pack. Now the Atlantic BFS using Q_ATL. We pop cell, IJ, it reaches the Atlantic. We check 4 directions again. We compute neighbor NI and J. We check bounds, whether ATL is unmarked, and height greater than equals current height. Atlantic BFS is also OMN. We mark ATL NI and J equals true. And push it into Q_ATL. We create result to store coordinates where water reaches both oceans. We loop through rows and columns, scanning all cells, OMN. We check if IJ is true in both pack and ATL. If so, water can reach both oceans. We append IJ to result. Finally, we return result. Time complexity. Setup, OMN. Pacific BFS, OMN. Atlantic BFS, OMN. Final scan, OMN. Total, OMN. Space, OMN. For pack, ATL, and queues. And that's the algorithm. Mark border cells, run BFS from both oceans, and intersect the reachability maps to get all dual ocean cells. Heights equals 1. Let's test our function using this input. This single cell represents the entire landscape. Our BFS approach starts from the Pacific, top/left, and Atlantic, bottom/right, edges, marking all reachable cells. Here, the only cell touches both oceans automatically. For example, cell 0,0 has height 1. It's on both edges, so water can flow to both oceans without moving. This output, 0,0, matches the expected result, confirming our BFS logic works even for the smallest grid. The algorithm correctly identifies cells that can reach both oceans efficiently. Let's have a quick recap. We're given a grid of heights, and we need to find all coordinates where water can flow to both the Pacific and Atlantic Oceans. Water moves from high ground to equal or lower neighboring cells, so the challenge is to identify which points can reach both sides of the map. The key insight? Instead of simulating water flowing out from every cell, we reverse the flow. We start from the oceans themselves and move inward, only climbing to equal or higher cells. This way, we explore where water could have come from rather than where it's going. 2 searches, one from the Pacific borders and one from the Atlantic, keep the logic efficient and elegant. We set up 2 visited sets, one for each ocean. From the Pacific borders, top and left, we run DFS or BFS uphill. From the Atlantic borders, bottom and right, we do the same. Finally, the intersection of those visited cells gives the positions that can flow to both oceans. We built a clean DFS helper, launched searches from each border, and collected results into both sets. The logic ran smoothly, and we executed the code on LeetCode without any errors. After running the solution, every expected coordinate appeared exactly as it should. The logic held up across all test cases, From flat terrains to complex slopes, all passing successfully. The real takeaway? Multi-source graph problems often become simpler when you flip the perspective. Think in reverse, propagate from the destinations instead of the sources, and you'll unlock a deeper intuition for reachability and flow in grid and graph challenges.